Today is the third installment of our series, and today we're looking at a topic which is a little bit more complex. We will be dealing with longitudinal data. And as you may remember, last webinar we dealt with regression analysis, and there are certain assumptions in regression analysis which are important in order for us to perform those. And one of those is autocorrelation. And today we'll be dealing with strategies for dealing with autocorrelated data. And the speakers for today, I'm your host, I'm Lukhanyo Nyati, and the speaker today is going to be Dr. Will Johnson. I will introduce Will a little bit later. I will just give a short presentation just to set the scene. And after that, I'm going to introduce Dr. Will Johnson, who then will take over from me. So just to set the scene, and these are some of the learning objectives that we have for today, to learn to introduce us to autocorrelated data, to introduce us to reverse causality, to introduce us to methods for longitudinal data. And you'll understand why I wrote this as we go through my short presentation. I'm trying to remove this. Okay, there we go, right. Now, just as a review, this is what we covered in the first two webinars. The first webinar covered descriptive statistics and hypothesis testing. And one of the key lessons that we can take from that webinar is the importance of power calculations in statistical inference. And we learned about different types of errors, errors that can lead us to falsely accept the null hypothesis, and others that can lead us to falsely reject the null hypothesis. And then the second webinar, we dealt with linear regression. And one of the key lessons that we can take from that presentation is the fact that we're dealing with association in our observational studies, and we cannot take association to be causation. And this is also very important in our language and how we write our papers. And there are also important assumptions that we need to take into consideration when performing linear regression analysis. And one of those that we're going to be talking about today is this concept of autocorrelation. Now, autocorrelation can be found in many different scenarios. And two of the scenarios that I've highlighted here, and I'm sure Dr. Johnson is going to go into more detail about this. When we're dealing with repeated measurements or longitudinal data, for example, when you are measuring children on a yearly basis or on an annual basis in a particular age bracket, you're measuring those children repeatedly over time. And then one of the important things, so just also to link it back to the previous webinar, where we were talking about linear regression, and just to remind us that we're talking about association. Now, and we're talking about association, which is different from causation. Now, one of the two important constraints to causation is confounding, which is something that we dealt with in the previous webinar, and also something called reverse causation. And in this particular case, longitudinal data or repeated measurements can assist. And I'm going to show an example of how longitudinal data are important in dealing with this matter or this issue of reverse causation. Now, as an example, I'm going to use an example of the association between systolic blood pressure and mortality, which is in old adults. So these are adults who are old, looking at about in the ages, for example, of 80 and above. And there's the observational data shows that lower systolic blood pressure in that particular age group is associated with higher risk of mortality. Now, there's a study, which is actually a trial, which was done, there's a paper which was published in 2016 in the Journal of American Medical Association. And this trial is called the Systolic Blood Pressure Intervention Trial. And they found something which is in contrast to what observational data show. And they show that lowering the systolic blood pressure to a target lower than 120 millimeters of mercury led to a 3% reduction in all-cause mortality in all those older than 75 years of age. Now, like I said, this is something which is in contrast with what is in observational data. So there's another study. So this is a study that I want to talk about. This study, which is now, the title of the study is Systolic Blood Pressure less than 120 millimeters of mercury associated with higher risk of mortality than systolic, this is not the title of the study. This is not the title, but this is in essence what they were looking at, the association between systolic blood pressure, low systolic blood pressure, which is lower than 18, and compare it to systolic blood pressure between 120 and 139 millimeters of mercury, in adults of over 80. And so this is actually their finding, and they find that, you know, in the group of participants where the systolic blood pressure was lower than 120 millimeters of mercury, that group was associated, you know, had a higher risk of mortality than the group with systolic blood pressure between 120 and 139 millimeters of mercury in adults over 80. Let me just check to see if I don't have the title of this particular study. Okay, so I will add the reference a little bit later just to show you the reference to this particular study. Now, coming to the point that I'm trying to bring forward, which is, now we've got two scenarios where one study showed that an association, which is lower, is associated with a reduction in all-cause mortality. And this other study, which shows that a lower systolic blood pressure is associated with higher mortality. So what these ones, they were trying to, you know, to look at and to test what actually is the issue, or rather, you know, to look at the previous study, which is the SPRINT study, and to validate the results from the study. And what they did, they looked at longitudinal data, which is from a cohort in the United Kingdom. And one of the things that they did was, for example, to plot. So we spoke about some of the things that you need to do in order to, you know, before you perform your modeling or your, you know, any statistical inference. And one of the things is to plot your data, just to get a sense of what the data look like. So one of the things that they did in this particular study was, as you can see, there are two panels of plots. You've got the left panel, which is the A and C, and then you've got the right panel, which is your A and your B and D. And so the left side of the panel are min plots, whereas if you look at the right side, they have modeled this using some form of a polynomial model. And what they found, now the blue is, so if you look at this, so these are individuals who have not died, who are alive, and these are the orange is individuals who have died in both plots. This is the model data, and they're showing the relationship between you know, time before death and systolic blood pressure. And what you can clearly see in this plot, and these are individuals who have died. The individuals who have died tend to have lower systolic blood pressure towards the time of death compared to those who survived. And you can see that in both the modeled as well as in the raw data. Now, this is attributed to, you know, to a number of factors: deteriorating nutritional status accompanied by chronic inflammation, which may tend to lower blood pressure levels at the end of life. So now we can see clearly in this, one of the questions that we need to ask ourselves is, what comes first in terms of the relationships or the associations that we're trying to establish? And clearly in the study, we can see, I mean, logically, one would think that the time of death comes after, obviously, the event of reduction in blood pressure. However, what the authors are suggesting is that as individuals come closer to the time of death, there are certain biological processes which take place, such as deteriorating nutritional status and chronic inflammation, which may lead to lower blood pressure. So by using what we're showing here, and the point that I'm trying to drive, by using longitudinal data, we can clearly try and see exactly the direction of this relationship, which if we only looked at a cross-sectional data point, we can have, that can lead to misleading conclusions about the direction of the association, because like the previous study, the PRINCE study or the SPRINT study, we showed that lower blood pressure may be associated with lower risk of death. When we're doing cross-sectional data, we're unable to deal with factors such as reverse causality. And this has been shown also in a number. So in essence, what the study is showing is done by these authors, and the authors are Williamson et al. And this paper was published in the Journal Circulation in 2017. They showed actually that the direction of the relationship is the fact that people towards the end of their life may have factors that influence their systolic blood pressure, which makes the relationship then not mortality being the outcome and systolic blood pressure being the exposure, but the other way around. And these are other examples here of cases where reverse causality may be noted. And we can see here, again, I've highlighted that the importance of serial measurements and how they can assist in dealing with issues of reverse causality. So this is just one of the scenarios where longitudinal data are extremely important, in that it can take some of the associations that we're establishing in observational studies, and we can take that further through multiple or repeated measurements to try and try and decipher exactly the directions of the relationships that we're establishing. So I thought that this would be important for us to set the scene. And at this point, I'm going to hand over to Dr. Will Johnson. And before I do that, I'm just going to read Dr. Johnson's bio. Dr. Will Johnson trained in human biology with a BSc and PhD from Loughborough University between 2003 and 2010, and in epidemiology during postdoctoral positions at the University of Minnesota's Division for Epidemiology and Community Health, the MRC Unit for Lifelong Health and Aging at UCL, and MRC Human Nutrition, and MRC Human Nutrition. His experience and expertise are investigating the etiologic factors that regulate human growth and development, the role of body size trajectories in obesity and related disease development, and secular trends in longitudinal processes and relationships. From conducting this research, he has developed advanced skills in the design and application of statistical methods to longitudinal data, particularly those pertaining to human physical growth and obesity development. His work is currently funded by the UK Medical Research Council via a new investigator research grant and the USA National Institutes for Health. He sits on the executive committees for the Society for the Study of Human Biology and the International Society for the Study of Human Growth and Clinical Epidemiology. At this moment, I'm going to hand over to Dr. Will Johnson.
Hi, everyone. Thanks for coming to this seminar. I'll keep talking and assume you can all hear and see me and see the slides. If you have questions, feel free to put them in the Q&A at any point, and Lukanya and myself will keep keep an eye on that, and I'm going to try and answer the questions as I go through the talk. So if anything isn't clear, put it into the question and answer, and we'll go through it that way. I'll also leave some time at the end for questions. My talk's kind of organized into two parts. One goes through longitudinal data and how to model longitudinal data using multi-level models. And the second sort of part of the talk is sort of examples of how you can extend those models in different ways, which I go through in less detail just because there's lots of different ways that the analysis can be extended. So I guess one important thing to explain before I start is that I'm not a statistician. I don't have a degree in statistics. I never formally trained in statistics. I've learned what I do through working with data, right? And it's through working with longitudinal data that you then become an expert or develop expertise in analyzing the data. So most of my slides don't have equations. If I show equations, I don't expect you to know what they will mean or to remember them. As I say with my students at Loughborough in the UK, the most important thing is you understand the concepts, right? You understand the concepts of this kind of analytical approach rather than the equation. The equations are largely not irrelevant, but it's the approach that's important, right? So okay, so when I talk about longitudinal data, these are the kind of data that I have worked with previously. They're just a few examples, but the important points, right? So if we looked at this plot down here on the bottom left, we've got systolic blood pressure plotted against age. And each of those different colored lines represent one person, right? And they're longitudinal data because that person, say this person here who's light blue, has been measured multiple times over age. Same with this example here, we've got weight, or maternal pre-pregnancy and conceptional weight. And these mothers have been weighed multiple times before and during pregnancy. So longitudinal data really occur when you measure some entity, it could be anything, multiple different points in time. I work with individuals, with data on individuals, on humans that have been measured normally at different points of age. But longitudinal data can occur when you take measurements on, I don't know, some country like gross domestic product, GDP, gross domestic product, and you take that every year. Or you might be interested in the, I don't know, or anything, I mean, in pigs or dogs or countries or continents or cities, any entity that's been measured where you've got some data at different points in time. Okay. So longitudinal data are structured, and they're structured as shown in this schematic. And this kind of hierarchy is important to understand. Longitudinal data can be thought of as having two different levels. So each individual in your sample, okay, will have been measured on multiple occasions, okay? And there could be any number of individuals and any number of occasions. And the occasions don't necessarily have to be the same for each individual. So for example, this individual 1 might have been measured, say at 1 year, 3 years and 8 years of age, but individual 2 over here might have been measured 10 times at 2, 3, 4, 7, 9 months, 10 years, 11 years, 12 years. So it's important to remember that you can have very unstructured data, any number of individuals measured any number of occasions, and those measurement occasions don't have to be the same. Okay, and we'll see later how multi-level models handle this kind of unbalanced data. The important point to take from this slide is that serial measurement occasions are clustered within individuals. Okay, so these measurement occasions are clustered within individuals, i.e. these occasions here, these measurement occasions are clustered within this one individual. And throughout this this seminar, I'm going to refer to occasions as being level 1 and individuals being level 2. okay? So measurement occasions level 1, individuals level 2. Now, when we switch to sort of a data set, the data looks more like this, right? So if you focus on this example on the left-hand side, this is what we would call a wide data set. Now, instead of just having Y, our outcome is now Yij, and that's essentially the response or the outcome at occasion I for individual J. So for example, individual 1, and they've been measured at occasion 1, occasion 2, and occasion 4. They weren't measured at occasion 3. So this individual's is 1, their first occasion, so this is Y11. At occasion 2, they're Y21, and occasion 4, they're Y41. And we can restructure that data for it to be in long format, as shown here on the right-hand side. So on the right-hand side, we see exactly the same data. It's now just in long format. We've got Y11, Y21, they don't have Y3 and Y41. So individual 1 has been seen, there's 4 measurement occasions, they've been seen on 3 of them. Now, it doesn't matter too much if you if you don't sort of understand what's going on here. The point is that in the formula for multi-level models, we use this I and J subscript. So when you see the equations or the limited equations I've got later on, they're going to have I and J subscripts, right? And this is what it's referring to, okay? So Yij is the response or the outcome at occasion I for individual J. So you'll see that later. Just try and get to my next slide. So essentially, multi-level models handle clustered data, okay, and the kind of clustering that we see in longitudinal data is when you have measurement occasions clustered within individuals. There's lots of other different types of multi-level data where you've got clustering essentially. And what we thought would be a useful exercise would be for 2 minutes maybe to have a think about other types of clustered data. I'm not going to give you any examples, but in the chat, in the Q&A, I'm going to give you 2 minutes. I want you to think and write examples in the chat of other types of clustered data. If you don't know what's clear by what I've just said, sort of put it in the Q&A. But have a minute and try and put a few things into the Q&A about other types of clustered data. So someone's just posted, would this include share prices on the JSE? You'll have, is JSE, does that stand for Johannesburg Stock Exchange, I guess? I'm assuming that's Johannesburg Stock Exchange. And I guess it would, right? Because you've got share prices that will vary throughout the day, okay? So in a sense, you can see share prices within the JSE as being longitudinal. So you would have serial measurements of share prices within that stock exchange. Now, ideally, what you'd have is other stock exchanges. So you'd have multiple stock exchanges with longitudinal data. So yeah, I mean, I could see that as being an example of longitudinal data where there's serial measurements clustered within individuals. The image that I'm showing on this slide kind of is actually demonstrates another type of clustering, right? So here I've got different clusters of individuals. So can anyone think of an example when you'd have clustering of individuals? So if you look at the image, you've got a red group and a green group. You know, what could those different groups represent? Individuals within different what? Exactly, right? So I was just scrolling down. So exactly. So you could have individuals from different neighborhoods. You can have individuals from different schools. You could have classes from different schools or classes from different universities. You can have countries within different continents. Siblings within households, individuals from different countries, patients from different clinics. All of those examples are also examples of clustered data. And as I talk through multi-level modeling, everything that I'm going to teach you essentially can be applied to other questions where you've got clustered data. So we're talking about multi-level models for longitudinal data, but you can also have multi-level models for other types of clustered data where you might have measurements on children from 20 different schools in Johannesburg, okay? So I think in one sense, my talk is about multi-level models for longitudinal data, but really if you want to expand that, it's multi-level models for clustered data. There was one question on here saying still not sure what meant by clustered, and really the simplest way to explain that is to look at the schematic, right, the figure that I'm showing now. So imagine that you did a study, right, and you wanted to recruit, I don't know, 800 children, but those 800 children were from 8 different schools in Johannesburg, okay? So the red people there represent 100 children from one school. The blue represents 100 people from a different school. The yellow represents 100 people from another different school. And that's clustering, right? The children are clustered by school. And it's important to acknowledge that clustering in analysis, because the school that people in the red go to might be very different to the school that the people in the yellow go to, or the school that people in the blue go to. There's very different characteristics of different clusters or groups of people. And the multi-level model sort of handles that and accounts for that differences between schools. Okay, so that's clustering in a nutshell. How many clusters do you need? I mean, most analyses will have 20 higher level units. So in my research, that might mean that I'd have a minimum of, say, 20 children. And each of those children would have multiple serial measurements. In reality, the data that I work with, I normally have more like 10,000, 20,000 children, 5,000 children, and each of those children will have maybe 4, 5, 6 measurements. I just put this slide in to say that actually you don't need that many clusters. I've published a paper where we've looked at children clustered within schools, and there were only 7 schools. So there are ways to get these models to work if you've only got a few clusters. So if we go back to sort of regression, right? So this is an example taken from my own research. So here we've got body mass index data. I assume everybody knows what body mass index is, BMI. It's essentially just a measure of weight for height. And these are longitudinal BMI data from one of the UK birth cohort studies that I work with. There's 200 people here, so I just randomly selected 200 people, and in total there's 623 measurements. Okay, so not all 200 people were measured at 5 time points. They weren't, and you can see that there were measurement time points at 16, 26, 30, 34, and 42 years of age. Okay. And if you were to just fit a normal regression model to these data, and I'm not going to dwell on regression too much because I think in the last seminar you were taught regression or someone spoke to you about regression. But this is just a general linear regression model. Okay, so your outcome is BMI. and you regress BMI on age, and you get two estimates, right? You get an estimate of the intercept, 17.857. Now that estimate of 17.857 essentially means what's the predicted value of BMI when the X variable age is at 0, okay? So this red line will cross through the Y-axis at 17.857. And you also get an estimate of the association of the slope. So 0.205 means that as age increases by 1 year, BMI is predicted to increase by 0.205. Okay. The numbers in brackets are the standard errors, but don't worry about those. And that's just a regression equation, which you hopefully will be familiar with. If you're not familiar with that and need more detail, then put it into the Q&A. The obvious problem here, right, is that we're estimating the constant when age is at 0, and there's no data down here. Okay, there's no data down here. So one of the common things that we do is we shift the age scale, or we shift the scale of the X variable. So all I've done here is I've taken the original age variable and I've subtracted 16 from it. I've created a new variable, which is age minus 16. So 16 becomes 0, 26 becomes 10, and so on. And now when we fit our regression model, our estimate of the constant, okay, 21.144, corresponds to this point here on the Y-axis when this regression line passes through the Y-axis at 0, okay? i.e., at 16 years of age, the average BMI is predicted to be 21.144. The slope hasn't changed. It's still 0.205, which it was up here. Okay. Now that's, in a nutshell, that's regression, right? You're taking some data, you're producing a scatter plot of your Y variable on the Y-axis against your X variable, and you're fitting a line of best fit. Now, in addition to having your intercept and your constant, you also have error, okay, or you have residuals. And these residuals here are illustrated by these red arrows. So imagine that this individual here was measured. This individual has three data points. So the orange circles, this person was measured at 30, 34, and 42 years of age. So that individual has three residuals, which are indicated by those red arrows. Now, every data point in this scatter plot will have a residual, okay? So there'll be 623 of them. Now, one of the key assumptions of regression is that the residuals are not correlated with each other over time. Essentially, what that means is that these residuals should randomly be positive or negative, i.e. above or below the line. There shouldn't be a pattern. Whereas here, they're all above the line, obviously. So we're violating assumption because they shouldn't all follow that pattern of being above the line. They should just be randomly above or below the line. In addition to being randomly above the line or below the line, the magnitude should be unrelated. Whereas here, obviously, the size of this red arrow or residual is related to the size of this one, which is related to the size of this one. So this is where you have autocorrelated residuals. And this naturally happens with all longitudinal data if you fit a simple regression model or a general linear regression model to them. The same would be true for the data for any of the other 199 children or individuals in the sample. And in essence, this is why you can't use normal or general linear regression for multi-level data, okay? You can't use it because these red arrows, these residuals are autocorrelated. And that's violating one of your 4 key explicit assumptions of general linear regression. So the question is, well, how do we get around this problem? How do we get around this problem that these red arrows are kind of related to each other? They're all positive and they're all of a similar size. The answer is to imagine a situation where the average trajectory or the average regression line or curve is shifted up or down for each person in your sample, okay? So if we were to shift this red line upwards for this orange person, their individual curve would be this orange line here, right? Okay, and you can now see that the red residuals, well, this one's negative, this one is very small, and this one's positive. So these residuals are now not correlated with each other. We still have these residuals where we've got differences between the individual's fitted line and the individual's data points. Okay, but these are now called level 1 residuals. They're level 1 because level 1 is the measurement occasion. Okay, so they're measurement occasion or level 1 residuals, and together all of those residuals summarize the within individual variance. So there's going to be 623 of these little red arrows. They describe the difference between each individual's trajectory or line and each individual's data points. And together they describe the level 1 or within individual variance. So there's a lot to take in there, but think of it essentially about shifting the line up or down for each person or each child to resolve the issue of autocorrelation of residuals. Okay. Now, of course, in addition to having these little red arrows, what we've essentially done is that we've created purple arrows as well. We've shifted this red line up by this amount, by the amount illustrated by this purple arrow, okay? And every person in our sample will have one of those purple arrows. Some will be shifted up, some will be shifted down to fit their data. Now, these are called the level 2 residuals. They're level 2 because level 2 is the individual level, right? So level 2 residuals describe the between individual variance, okay, or the differences between individuals in BMI. Okay. It's called a random intercepts model because the model is essentially estimating a different intercept for each person, okay? So, for example, the intercept for this orange person would be around 25, a BMI of 25, okay? But someone down here might have an intercept of 16 or 17. Okay. This slide's really important because this is what multi-level models are doing, right? They're taking what used to be one source of variance in normal regression, and they're now saying there's 2 sources of variance. In normal regression, you have red arrows, that's the variance. Now we've got 2 sets of arrows describing the variance. We've got the level 1 or within individual variance, and we've got the level 2 or between individual variance. So this slide is really important. Now, I've put the equation in here on the right-hand side. I don't sort of expect you to, or you don't necessarily need to know this equation, but what it's showing is that it's showing you essentially what the model looks like. The fundamental difference between this equation and the equation that you will have seen previously for a general linear regression model is that now the intercept or the constant comprises 2 parts. Okay, so beta 0 ij, okay, or beta 0 ij now corresponds to beta 0, and beta 0 is the average intercept, okay, in the sample. So it corresponds to the predicted BMI at 16 years of age, you know, the mean BMI at 16 years of age for your sample. But we also have the U0Js, and those are the random effects which describe how each person's intercept is different from the sample average intercept. Okay, so think of it this way: we've got beta 0 ij equals beta 0 plus U0J. Okay. Beta 0 would be this value here of around where this red line crosses through the y-axis of around, say, 21. The intercept for this orange person would be beta 0 plus U0J, which is the size of this purple arrow, and that gives the intercept for this person. So the intercept for this person, the orange person, for example, is equal to B0 plus their U0J. I'd ignore the error bit for now. So there's a lot to take in here, but essentially what you have is, this is called a fixed effect. So the beta 0 is a fixed effect because it corresponds to the sample average trajectory. And you have a random effect, which is the U0J, and that describes how each individual is different from the sample average trajectory or line. This is sometimes called a random effects model because you've got these U0Js or random effects. Sometimes it's called a mixed effects model because you have fixed effects and random effects, i.e. mixed effects. But you'll see that the basic assumptions for both parts of the model were the same, okay? So that the level 1 residuals, i.e. the red arrows, they're assumed to be normally distributed with a mean of 0 with some variance. And the level 2 residuals, or the level 2 random effects, are assumed to be normally distributed with a mean of 0 and some variance. The best thing to do is to, in my mind, is that when you fit a model is to plot the level 1 residuals against age or against your time scale to check that they should have a mean of 0 across the entire age range. And if they don't, as shown here, your model isn't working very well. So here's your parameter estimates. And just as in normal regression, right, you get your estimate of the intercept and you get your estimate of the association or the slope, okay? So this is exactly the same as what you'd get in normal regression. And so you've got the estimates that you get in normal regression, and then you've got estimates of the variance at each level, okay? The red arrows represent level 1, okay? So that's the measurement occasion, okay? And the purple arrows summarize the variance at level 2, okay? And that's the individual level, okay? We've got individuals, measurement occasions clustered within individuals. And for each of those, we get an estimate of the variance. Now, these variances are being estimated using squared residuals as you would do in a normal regression model. But we can take the square root of those estimates to get some values that kind of make sense on the original scale, on the BMI scale. So the value of 2.8 kilograms per meter squared, what that means is that essentially it's the average difference between any given 2 people individuals' trajectories, okay? So on average, people's trajectories differ by 2.8 kilograms per meter squared. Okay? That up-down shift is on average, the difference between individuals is on average 2.8 kilograms. The variance estimate here for the red or the within individual variance of 2, what that means is that on average, the difference, on average, the can't think of the word, the distance between any given data point and that individual's line is 2 kilograms per meter squared. So here, this is the average difference between individuals, and this is the average difference between an individual's data point, one data point, and their fitted line. Okay. So 2 kilograms per meter squared, that's essentially error. That's the average error in the model. And with all growth modeling, what we want to do is try and get that error down to about the same as measurement error. Okay. So what these models are essentially doing is partitioning variance. they're partitioning variance between the two levels. Instead of having one source of variance, we now have two. We've got within individual and between individual variance. And as you see here, we've got an estimate of each of those. It's quite easy to then think about, well, how much of the total variance in those BMI measurements that I showed you is because of differences between individuals. Okay. So let me just repeat that. How much of the variance in the BMI measurements is because of differences between individuals? Okay. And we could work that out by taking the differences between individuals. So that variance is 7.9, and dividing that by the total variance, which is 7.9 plus 4.1. And that gives us 0.659. Now, if we multiply that by 100, we get 65.9%. So call it 66%. What that means is that 66% of the total variation in BMI in that sample was due to differences between individuals or between people. Okay. 66% of the variance in the BMI was due to differences between individuals. And that's why we need a multi-level model, right? If this number was very low, okay, then there wouldn't be many differences between individuals, and we wouldn't need a multi-level model because there wouldn't be any clustering, okay? Okay. I guess I'll say as well that, I mean, this is known as the variance partitioning coefficient. There's also a thing called the intra-class correlation coefficient, and that's the expected correlation between two measurements in the same person. Now, in this simple model, the VPC, the variance partitioning coefficient, and the ICC, the intra-class correlation coefficient, is exactly the same, okay? i.e. the expected correlation between two measurements in the same person is 0.659. But be aware that the VPC and the ICC aren't always the same with more complicated models. So we've gone through this sort of example of having a random intercepts model, which is kind of your simplest type of one of the simplest types of a multi-level model. We're essentially allowing each individual, the line to be shifted up or down to be higher or lower for each individual. Now, sometimes that's enough, and sometimes it's not. I mean, with BMI, we might have some people that start with a very low BMI, but end up with a very high BMI, or vice versa. And the natural thing that we want to do, instead of just allowing the line to be higher or lower for each person, we also want it to be steeper or shallower for each person. So this represents this schematic, right? So we just talked about this figure over here. But reality, what we want to do is we want to allow this orange line to be steeper or shallower for different people. And here I've shown that this orange line is actually steeper, okay? So their increase in BMI over age is greater or faster than on average in the sample. And how that's done is represented in this figure. So we have a sample average trajectory. We have this black line, this thick black line that demonstrates sort of that average curve in the sample, or the average line in the sample. And then we have different individuals. If we focus on individual one, okay, well, individual one, they've been shifted upwards, their random intercept is higher, okay? So this is your U0, U01 or U0J. So their curve, their line has been shifted upwards, and that's what we were doing in the random intercepts model. But now we've also got this term up here, which represents a random slope. And what that is saying is that in addition to shifting this person's line up, we're also making it steeper. Okay. So each person now has an estimate of the random intercept and an estimate for the random slope. And that allows essentially the line to be completely different for each individual in the sample. Now, this is what the model looks like when you have these two random effect terms. We have one random effect term for the intercept and we have one random effect term for the slope. So we have two sets of purple arrows. So the intercept of person J is equal to the fixed effect, B0, okay, and that applies to everyone, plus the random effect, which is person specific. Similarly, the slope, the association between BMI and BMI and age for person 1 is equal to the beta 1, the fixed effect, okay, which is the sample average, plus the random effect, which is person specific. Now, obviously, by allowing a random slope as well as a random intercept, this level 1 variance, or this error term, has reduced, okay, because we're giving individuals more flexibility. We're giving the model more flexibility to fit the data. We now have two level 2 residuals, two purple arrows, and both of those terms, both of those sets of residuals are assumed to be normally distributed, okay, with a variance. Don't worry much more than that. So they've got a variance, okay. What you also have though is this covariance term, and you can think about it this way, okay. So think about it that every individual in your sample has a random intercept and a random slope, and that allows their line to be higher or lower or steeper or shallower, okay. But we can plot the random intercepts against the random slopes, okay. So this person up here, they had a very high BMI on average, and they had a steep slope, okay. Someone down here had a low BMI on average, and they had a shallow slope, okay, a slow slope. And this estimate of the covariance essentially corresponds to a correlation. And we've got a correlation between the random intercepts and the random slopes of 0.298. In simple terms, what that means is that individuals who have a higher BMI gain more BMI over our timescale than other people, okay? People who have higher BMI have steeper slopes, okay? People who have higher BMI, their BMI gain over that age scale, that time scale, is faster. You just need to be careful that when you're looking at this correlation or covariance, you interpret this alongside the sign of beta 1, the sample average slope. So for example, if BMI decreased over age on average, then a positive correlation or covariance could indicate that individuals with higher intercepts have less negative or flatter than average slopes. That kind of takes a while to get your head around, but I think the main thing is that you understand that you've got two random effects, random intercept and a random slope, and those two things can be correlated, okay, as shown here. So I've put this slide in just to show you some individuals' data. So this is illustrating, I've picked out 9 individuals. The orange data points represent the observed values, and the green lines are the fitted trajectories or the fitted curves for each person. Now, theoretically, these green lines range from -infinity to +infinity, and we could plot them that way, right? We could plot the line from, I don't know, 0 to 100 if we wanted for each person. We're doing it from 16 to 42, or they would be from 16 to 42 theoretically. Now, number 7, this person in the bottom left, only has one data point, one observation. But you'll have to trust me that they do have a random intercept and a random slope, okay? And we could produce a green line for them, okay? All the way through this range from minus to +infinity. So even if someone only has one data point, we're still able to estimate their line, their regression line, okay? And if you're interested in sort of how the model works and how it does this, I can send you some literature, but it works on the assumption that the data are missing at random, i.e. the pattern of missingness is related to observed variables, which is nearly always the case in longitudinal studies. And that's why this standard MI this technique can be used. So every individual in your sample, you have a fitted line, okay, or a fitted trajectory. Another useful thing that you can sometimes do is to do this kind of, I think it's called a caterpillar plot, that shows the random slopes. Okay, so here we're showing the random slopes for all 200 people, and we've ordered them from the lowest to the highest. Okay, so this person up here with this point, they had the steepest BMI slope, and this person down here had the least steepest BMI slope, the shallowest BMI slope. Now, in this example, you might think, well, why are you doing this? But imagine a scenario where these random slopes were, say they were representing the association between income and obesity at the country level. Okay. So each of these estimates corresponds to the association between income and BMI, say. So the outcome is BMI, the independent variable is income, and the data is clustered by country. So each of these points represents a country. Now that might be interesting to look at to see how the relationship between income and BMI differs according to different countries. We might think that up here we might have, I don't know, maybe low middle income countries where greater income is related to greater obesity risk or greater BMI. And down here, we might have higher income countries, perhaps, I don't know, where higher income is related to lower BMI or lower obesity risk. So I just wanted to put this plotting because I think if you're working with data that are clustered by country or school or geographic region, I think it's really useful. So when we had a random intercept model, the between individual variance was constant across age. And it had to be because all the individual trajectories were parallel. So think of it this way, there was just lots of lines parallel like this. So the variance or the difference between those lines was the same at every given point on the X scale. Now, if we allow a random slope, that between individual variance can change over time, or it can differ according to age. If you imagine a scenario where we've got lots of individual trajectories that kind of span out like this, as you move across age, you'd expect the between individual variance to get greater. If they all fanned in together, the between individual variance would decrease over age. In the example that I showed you, the between individual variance actually increases between between 16 and 42 years of age. This is the function of how it does that. You don't need to worry about why that's the equation, it just is. But if you know the topic, this sort of pattern probably won't be surprising. It makes sense, right? Between individual variance or differences between individuals in BMI increases with time. Okay, so I'm reaching the end of the first part. Assume that you've developed your multi-level model and you're happy with it. The next thing you might want to do is to see if there are differences in that average trajectory or that average relationship between BMI and age according to some other explanatory variable. And you do this exactly the same way you would with a normal regression model. So here I've added in a sex term and a sex by age interaction term, okay? And those estimates essentially tell us how the sample average trajectory differs according to sex. So this 0.118 tells us that females have a 0.118 unit higher BMI at age 16 than males. And this other estimate here tells us that the rate of change, the rate of BMI change per year is 0.057 units lower in females compared to males. And that's why the orange line kind of starts to fall away from the blue line. But you can include any variable in this, a level 1 or a level 2 variable, in exactly the same way you would in a normal regression model. and you interpret these estimates in exactly the same way you would as in a normal regression model. So you can bring in explanatory variables or covariates to describe how the average line differs. In our instance, we looked at how it differs between sex. But you can also do something a bit more complicated and see how the level 1 variance differs according to different variables, i.e. how does the error or the within individual variance differ between males and females. And what you'll see here is I've got an error estimate if the person is male and an error estimate if the person's female. And you can see that the variance or the within individual variance, now there's a within individual variance for females and one for males. Now this is called complex level 1 variation. In most instances, it doesn't make sense to do it. But imagine a scenario where you have a mixture of measured and self-reported data. So the measured data, so let's say they've measured their weight and their height, say their weight, and self-reported, they've just asked people, well, what was your weight? What is your weight? Well, what you'd expect, so this is one person with 1, 2, 3, 4, 5, 6, 7 data points. You would expect that the residuals for the measured data would be smaller than the residuals for the self-reported data, because there's going to be error or more error in the self-reported data than in the measured data. And by producing this kind of model, we can have different estimates for whether the data were measured or self-reported. And by doing that, we're improving our model and our ability to fit good curves or good trajectories. So that's kind of a whistle-stop tour of multi-level models. And essentially what they're doing is they're partitioning variance, in our instance, between 2 levels. They're useful in life course epidemiology or the research that I do, because they allow you to simultaneously model individual trajectories, a sample average trajectory, and test the effect of explanatory variables on that sample average trajectory. The model properly accounts for the hierarchical nature of the data, i.e. the fact that there's this auto-regressive structure, and they can easily handle missing data or unbalanced designs. So the key principles apply to any type of longitudinal data and any type of cross-sectional data where there's some inherent multi-level structure, i.e. there's test scores, i.e. test scores within scores. So that's the end of my first part. I'm gonna throw a question out there and then just have a glass of water while you think about it. So we've got a normal regression model. So we've got fixed intercept and slope, and essentially what that means is that's just, we've analyzed longitudinal data, the longitudinal data that I showed you up here, actually, these longitudinal data. If we analyze those with just a normal general linear regression model, our estimate for beta 1 would be this, okay? And our estimate, if we had a multi-level model with a random intercept and slope, would be this. Now they're very similar. So the question is, well, does it really matter? Does it matter if you use a multi-level model or a general linear regression model? Why don't you just use a general linear regression model, because the estimates are very similar? Which leads me on to this slide. So here we've got a sort of a silly example. We've got hot dogs eaten in 10 minutes versus age for, what's that, 5 different people. Josh, Michael, Jessica, Faith, and Marcus. And if we were to analyze these data with a general linear regression model, the association would be this black line, right? i.e. as age increases, hot dogs eaten in 10 minutes decreases. So there's a negative association, i.e. older people eat less hot dogs. It should look like that, okay? Within each person, as age increases, the hot dogs eaten increases. And if you were to analyze the data with a good multi-level model with a random intercept and random slope, you would actually find the red line, that positive relationship, not the black line, the negative relationship. So in essence, if you take nothing away from today, just remember this screenshot, this slide. This is why you need multi-level models if you've got longitudinal data. So I'm gonna really quickly go through how these models can be extended. My slides will be made available, I'm sure. And if you have any questions about these kind of extensions, then you can always email me. So we've talked about multi-level models with 2 levels. You can have 3 levels. So you might have observations clustered within states, clustered within regions, or we might have observations clustered within children, clustered within schools. So you can have more than 2 levels. You can have a cross-classified structure, i.e. we've got lots of individuals here, and say the first 4, they all attend, or they're all from the same neighborhood, but they're from different workplaces, okay? So there's a cross-classified structure. Or you can have a multiple membership structure where you've got patients clustered within hospitals, but some patients attend more than 1 hospital. So this patient here attends 2 hospitals. So in multi-level models can handle lots of different structures that I haven't spoken about today. I just wanted you to be aware. And that's an example of a complex structure. If you're interested, you can read that paper. Multi-level models can handle non-linear relationships, i.e. these lines here are not straight lines. And the simplest way of doing that is, in our example, we could have had age and age squared. There's lots of different ways to fit a non-linear relationship. And I won't go into more than that, except, of course, it can be done within multi-level models. Here's an example of, if you were interested to read more, here's one example of a study that's fitted non-linear relationships. Of course, if you fit a curve, a non-linear curve, i.e. this black line, you can then also work out velocity and acceleration based so that you can take the first derivative of that black line and you can get the velocity. You take the second derivative, you get the acceleration. And that's been used in papers like this, where here these black points, so this line here is for males. This first black point corresponds to the point where depressive symptoms were increasing most rapidly. And this line here, this point here, corresponds to the point where depressive symptoms were highest. Now they've worked out where these points occur by looking at the first derivative, by looking at the velocity curve. You might be interested in working out other traits. For example, you could fit individual BMI curves and work out things like, well, how long have they been obese? And will they've crossed through this threshold at this age, so they were obese for this duration of time. And this AUC, that was their exposure to obesity, their total exposure. You can, in addition to fitting smoothed curves, you can describe relationships between, say, BMI and age using broken sticks or linear splines. And these are really popular in epidemiology. So that's just one way of essentially describing a nonlinear relationship, but by using a series of smoothed lines. You can then relate characteristics of your multi-level model to some distal outcome. You might, for example, be interested in how these different parameters, so these rates of change in BMI for each person, are related to something like blood pressure, some distal outcome. And you can do that within one model. Okay, so you can develop one more complex model that does it all in one. You might be interested in seeing how the within individual variability, so the level 1 variance, is related to some distal outcome. And you can do that also within one model. Today we spoke about having general linear, or multi-level models for outcomes that were normally distributed and continuous. But you could have a multi-level pro-bit model or multi-level logistic model. If you can develop you can have a multi-level model for any outcome distribution, essentially. So this is a multi-level binary logistic regression model, as an example. Very quickly, you can model, I talked about modeling BMI, but you might have a model where you've got two processes. So you've got one model for BMI and one model for, say, systolic blood pressure. And you can actually fit those two models together and see how the parameters for BMI are related to the parameters for blood pressure. And then very quickly, you can extend multi-level models into a structural equation modeling framework to fit them as latent growth curve models. So a multi-level growth curve model is essentially exactly the same as a latent growth curve model. And if you have a latent growth curve model, you can extend that to a growth mixture model. And my final slide, I think, is this schematic showing, I mean, you might have read papers where you've read something like, oh, the authors might have said, oh, we developed a group-based trajectory model, or we developed a latent class trajectory model, or a growth mixture model, and we found 5 classes or 5 distinct groups of individuals, and you'll have a figure like this. This is just an extension of multi-level modeling, okay? And if you want to learn this kind of group-based modeling, I would start with multi-level modeling, and that's why I put it in here. In terms of resources, the Centre for Multi-Level Modelling at the University of Bristol is the best place to go to look online to start this. There's a couple of books here on the right that I have used when I started learning multi-level modelling, but they're kind of written by statisticians. I have a chapter out in this book here, Human Growth and Development, called Modelling Growth Curves for Epidemiology. And that's perhaps a nice sort of overview of approaches you can use, and essentially the basis of my talk today. So sorry that last bit's been rushed, but hopefully that's been useful to some of you. I'm happy to take questions. If you have questions via email, you can get my email from Lucanio. Thanks for listening.